Hello, welcome to our channel for probability and statistics. In this video, we will talk about the trade-off between type 1 and type 2 errors in hypothesis testing. So we know type 1 error actually is the probability of rejection of a null hypothesis. So when actually the null hypothesis is true. So we denote alpha for this error. Actually, its error will be very low, is expected about 0.05 in most cases. So we will set alpha is 0.05 or lower than 0.05. And for instance, the new vaccine may be no better than the one now in use. So the one now in use is a hypothesis H0, and we test an alternative which is better than H0 or H1. And we set if we get more than 8 surpass the 2 years period in the data, then we will reject the H0. But actually the H0 is true, and the new one is not better than the old one. So in this case, we commit a type 1 error. And a type 2 error is the other side. It is the non-rejection of a null hypothesis, and when actually it is false. So in the last example, if we set 8 is the critical region, so we get the few of the group surpass the 2 years period, then we will not reject the null hypothesis. But actually, the new machine is better than the old one. We just get the sample is below the critical line. So we do not reject the null hypothesis. So in this case, we commit a type 2 error because we failed to reject H0, but actually it is false. And people, of course, hope both the type 1 and the type 2 error which will be lower for both. But actually, it is a trade-off between type 1 and type 2 errors. Because if you want make type 1 error less and less, then you can just reduce the critical region. Reduce the critical region this one. We can set the critical line to the right. So for example, this is the critical line for the 8 positive in the sample. Then we set critical line to the 10 or 11 here. So this area will be less, right? So this is the critical region for the type 1 error. But same time, for a given hypothesis H1, this line to the right here will make yellow region bigger. So yellow region is beta, which means we do not reject the H0, and when actually H1 is true. So this figure shows very clear that alpha and beta are the trade-off for the given H0 and H1. But of course, people may say, we can just set H1 here, then the shape will look like this. And even we can set H1 here, then both the shape will not overlap. Then actually there's no alpha and no beta. So if you get a sample here, you will accept H0. If you get a sample there, you will get H1. And no any type 1 and type 2 error, right? But actually, if you have very distinctly H1 and H0 and H1, actually you do not need a statistical hypothesis testing, right? Hypothesis testing just for the case, for the circumstances, people are not sure. People are not sure, and maybe H0 is true, maybe H1 is true. So this is the requirement of hypothesis testing. So we need a random sample to get hypothesis testing, and for sure we will have alpha and beta. We will have error for both types, right? But actually these two types of error are trade-off. You cannot get both. You have to increase one of them when you want to decrease the other, right? And next we will show examples to illustrate numerically of the trade-off between type 1 and type 2 errors. So in this example, for example, we set 8 is the critical limit. Then in a Poisson distribution, when the probability of type 1 error is that you get a sample has more than 8 positive, when actually the null hypothesis, this is the success rate P, 1 of 4 in a Poisson process, in a binomial process, is true. So we can get this probability is x larger than 8 when P is 1 of 4. So this binomial distribution probability is about 0.04 for the type 1 error alpha. And in the same sample, we can calculate the beta. So beta is the H1 or alternative hypothesis is 1 of 2. And if this is true, then we get the sample of positive 8 or fewer in the group. So the beta probability is type 2 error equals the probability of positive less than 8 from the sample when actually the H1 hypothesis or the probability of 1 of 2 in each binomial process is true. So this probability is about 0.25. So we just remember in this case, probability of beta is 0.25 and the probability of alpha is 0.04. So next, when we change the critical limit to 7, then we calculate again. So in this case, alpha is the probability of you can get 7 or more when the success rate is 1 of 4. So when the null hypothesis is true. So in this case, alpha is 0.1, is larger than 0.04 when the critical limit is 8, right? But beta is 0.13, which is smaller than 0.25 when the critical region is 8. So here alpha increased but beta decreased. This is a clear trade-off. So if we set, for example, critical limit to 9 or 10, of course you can get a smaller alpha than 0.04, maybe 0.02. But you can get a even larger beta than 0.25, right? So the question is, both alpha and beta cannot be omitted, and they have trade-off. So which one is more important for the small alpha or small beta? Which one you have to choose? So this depends on the context or the research context or the research question you are interested in your subject. So usually a small alpha is favored when the significance region is very serious. So what this means? If you reject the null hypothesis and this area will be very important, very serious. What means, for example, if you want to send the criminals to jail, this is very serious because if innocent people were sent to jail, it's very serious, right? The human rights, the people, human being is the most important. So we want to eliminate the case of innocent people being sent to jail. So we will have to make this error as small as possible, maybe 0.001. So maybe here. So which means the people sent to jail are mostly correct that they commit a crime, right? We do not want to make innocent people. It's only 0.001. Only one of those people are wrongly sent to jail. This is what we want to hope, right? But if a small beta, if you want to favor it, in this case, when missing the suspect is serious. So if we do not want to miss any suspect, even this a little suspect, this is wrong, then we want to send this to critical region. But in this case, the example is like potential adult contents for children. So in this case, we want to set a critical region left side, maybe move to here. Move to here. We want to get a very, very low beta. Very low beta. Why? Because the content, if actually it is adult contents, which means H1 is true. But if we miss the two reject null hypothesis, then it is very critical because the children will see the adults. But in this case, we set here, critical here, region here, alpha will be bigger. Alpha, because this line will be here, then the yellow area will be less, but the blue area will be more, will be bigger. So which means there are many wrongly rejected cases. So many contents, even they are not adults, but we take them as adults, right? But if it is adults, of course, they are very likely they will be rejected, right? So the beta will be smaller. So beta is the missed adult contents. We will hope the missed adult contents rejected will be smaller as possible, right? Thanks for watching.